friends, welcome to VTeach. So in today's class, we are going to derive the expression for strain energy when it is subjected to shear. Okay, so in our last class, we derived the expression for strain energy, but when it is subjected to axial load, that means a normal load. But now it is subjected to a shear. Okay, so if a member is subjected to some shear, what is the strain energy stored in that body that we have to derive? So for that, I am considering a small element. So this is the small element that I am considering. Okay, the length of the element is ds. Okay, so once I apply this shear load means it is the load parallel to the surface of the body. Okay, so this is the load. If you are applying the load in this direction, then that is the normal load or perpendicular load. Okay, but here how I am applying the load? This is the surface, and parallel to the surface I am applying a load Q. Okay, so if I apply a load parallel to the surface, then what happened? Initially it is a straight line, but now because of this Q loading, it is converted into this dotted line. So after the application of load, this is the position of the body. Okay, so initially it is straight, but after the application of load Q, it is converted into this inclined line. So what are the changes happen now? Initially this is the point, top point. After that it is deformed up to here. So that change in length, that change in position is represented with delta. Okay, and in terms of angle, so here let's say gamma is the angle. Okay, so initially it is a straight line. If I am considering in terms of angle, it is deformed by certain angle, that is gamma. Okay, so here you can see I am considering a small length of element ds that is subjected to a shear load Q. So because of that, it is causing a small deformation of an angle gamma and a shear deflection of delta. Okay, so these are the considerations I am taking. Okay, I consider a small element of length ds subjected to Q. Because of that, gamma angle has been created and delta is the deflection applied. Okay, so now by considering this, we have to derive the expression. So what is the work done? So work done means what is the load we applied and what is the strain it occurred. Okay, if I apply a load P, because of this strain has been occurred. So work done means it is the triangle below this load and its extension curve. Okay, so half into load into strain. This is in case of a axial load. So now what is the situation? Here I have applied a Q load, shear force. So because of that, the delta is the deformation. So half into Q into delta. So that is the work done. So strain energy is nothing but equal to work done. So that is half into Q into delta. Okay, so now we will make some modifications here. Here if you observe this gamma, if I take tan gamma, what is the formula for the tan gamma? Opposite side, that is delta divided by adjacent side, that is ds. So this is the formula for the tan gamma. For the smaller angles of gamma, this gamma angle is not too much. It might be some 1 degree or 2 degrees, that's it. So for the smaller angles of gamma, we can write tan gamma as a gamma. Okay, if the gamma is small, then tan gamma is equal to gamma, that is equal to delta by ds. If I want delta, that is gamma into ds. Okay, so this is the formula for the deflection, gamma angle into that length of the member. So like that we have to obtain the expression for delta. So here delta is equal to gamma into ds. So I just substituted this value here. Okay, and but we know the formula for the shear strain. What is the formula for the shear modulus? So shear modulus G is equal to shear stress by shear strain. Okay, so that change in angle is nothing but the shear strain here. So shear modulus is equal to shear stress by shear strain. So from this, shear strain is equal to tau by G, shear modulus. Okay, or modulus of rigidity. So from this, gamma is equal to tau by G. So tau means it is the stress. So shear stress is equal to shear force by area. Okay, so normal stress is equal to load by area. Shear stress is equal to shear force by area. So that is why tau is equal to Q by A. So I substituted the value here. It is actually tau by G. In place of tau, I am substituting Q by A. So Q by AG. Okay, so this is the formula for the shear strain gamma. Okay, so in this equation, half into Q into gamma into ds, we have to substitute the gamma value as Q by AG. Okay, so half into Q, I am just substituting it here. This is the same equation. I am just substituting the gamma value. So half into Q into gamma value is Q by AG into ds. Okay, so that is equal to Q square into ds by 2Ga. So this much of strain energy is stored by that small element we considered. We considered a small element, right? So that small element is storing this much of strain energy. Q square into ds by 2Ga. What about the entire member? Okay, this is the actual member. So in this entire member, I considered only a small element. This is the small element I am considered. So on this small element, this is the strain energy storing. So now for the entire element. So for that we have to integrate it. So L is the, let's say L is the total length of the member. So from 0 to L we have to integrate. Then we can apply this strain energy for the entire length. Okay, so that is the meaning of integration. Why we use integration? We have to calculate some parameter for a small part and we have to apply that for the entire part. There we use this integration. Okay, so now we calculated strain energy for a small element and now I am applying that strain energy for the entire element. So U is equal to integral 0 to L q square into ds by 2ag. So here q square, so U is equal to q square by 2ag. These all are constants. So I am just taking them out. So integral 0 to L ds. Okay, so there is nothing. Nothing ds means it is a 1. 1 into ds. So integral of 1 means it is the constant. Okay, so in that s place we have to substitute the L value once and minus 0 value again. So as it is 0, there is no need to substitute. So now in the place of 1 we have to substitute the upper limit L. So now it is converting into q square into L by 2ag. Okay, this is the strain energy stored in a body. So previously what is the strain energy stored in a body because of axial loading? So that is p square L by 2ae. Okay, this is because of the axial loading, previous case. So here also it is very similar. In place of p means normal force. Here q means shear force. L is same, 2a is same. G means shear modulus, that is with respect to shear stresses and shear strain. Here E means with respect to normal stress and normal strain. Okay, so every equation will be like this only. What is the load applying, that will vary, and what is the property of the material, that also will vary. Okay, so here now this is the formula. Again, if I want to convert this in terms of a shear stress and shear strain, then we can do just like the previous case. So what is the actual equation? So q square into L by 2ag. So now first I am differentiating the half. Then we will remain with, I am writing q by a. So q by a is gone. So what is the remaining value? Q into L by G. Okay, so now this is the remaining value. So if I multiply this with a by a, area into area, what will happen? Half into q by a, shear force by area, that is the shear stress tau, into, so the same situation we have to observe like this, q by a once, so q by a is the stress, into, what is the remaining value? Area into length, that is the volume, divided by G. Okay, so this can be written as tau square by 2G into volume. Okay, so this is the strain energy stored in a body. Okay, from this equation only we are deriving this equation here in the terms of a load, length, area and shear modulus, but here only stress and shear modulus. Okay, this is the strain energy. If you want strain energy per unit volume, then what is the formula? So per unit volume means we have to divide this entire equation by volume. Now we will remain with tau square by 2G. This is the strain energy per unit volume and this is just the strain energy in the entire body. Okay, so this is the strain energy when a body is subjected to shear. So similarly, we will also see what is the strain energy stored in a body when the member is subjected to bending. Okay, so here we have a beam or some member. Now we have applied some load, because of that bending has been occurred. So because of that bending, what is the strain energy stored? Okay, so for that situation, so here also I am considering a small element. This is the element I am considering. So initially it is a straight one. Okay, but I am applying a moment m like this. On both sides I am applying a moment m. So because of this moment, what happened? Now this straight line, the straight curve has been converted into this circular arc. Okay, so this line is before the application of moment. After the application of moment, it has been converted into this shape. Okay, so now we will see what are the variations. The initial length of the bar is dx, let's say. Okay, so this initial length, the center line length of that member is a dx. Okay, this curved length is the ds value. Ds means it is the straight length, and after that it has been converted into curve. That curve length is ds. And what is the angle? So what is the angle between the straight lines? Initially this is the straight line, after that this is the straight line. So what is this change in angle? That is d theta. Okay, what is the initial length and what is the final length and what is the change in angle? Okay, so those are the things now I am considering. So here if you see, if this angle is theta, then this is angle also equal to d theta. Okay, why? We have two forces with an angle theta. Now I am drawing the perpendicular for these two forces. For example, for this force I am drawing a perpendicular. Okay, so similarly for this force also I am drawing a perpendicular. Okay, so for these two members are the exactly perpendiculars. So then the angle between them will not change. If this is theta, this is also theta. Okay, so here also we are applying the same condition. This is the for these two lines are the perpendiculars. So that is why this is also equal to d theta. Okay, so now let us see how to calculate the strain energy. So these are the considerations. So here work done. So work done is equal to half into what is the external force we are applying. Here we are applying the moment. Okay, so that is the work done. What is the external effect we are giving and what is the change that has been occurred. So because of this m moment external effect we are applying, because of that the angle of rotation has been occurred. Okay, that means the member has been rotated. So half into moment into rotation. So that is the work done. So work done means nothing but it is the strain energy. Okay, so now half into m into d theta. This is the formula for the strain energy. So if you remember the bending equation, we have a bending equation, m by I is equal to sigma by y is equals to E by R. Okay, so this is the bending equation. So here now I am taking these two terms. Okay, so I am taking only these two terms. So from these two terms 1 by R is equals to m by EI. Okay, so 1 by R, wherever you see 1 by R, you just substitute with the m by EI. But before that one more step. So what is this d theta? Okay, so what is the d theta? Let's say this is the arc. So here it seems to be like this, right? This curved length after the deformation, its length is ds and the radius is r. This angle is d theta. Okay, we know the formula to calculate the arc length. So what is the arc length formula? So this arc length ds is given by radius into angle d theta. Okay, so this is the formula for this ds. So from this d theta is equal to ds by r. Okay, so here in the place of d theta I am substituting ds by r. So again in the place of 1 by r I am substituting this m by ei. Okay, so this is the formula. In this 1 by r I am taking separate. So in place of m by 1 by r I am substituting this m by ei. Okay, so now if you multiply m into m square divided by 2 ei into ds. Okay, so this is the strain energy stored in a body. It is not for the complete body. We have assumed a small element. So on that element this is the strain energy stored. Okay, so now coming to the entire member. So again same, after this entire member we have considered only a small part. So on this part we have applied a moment. So it has been deformed. So what is the strain energy stored in this small element? Just now we calculated. Now we have to apply that strain energy for the entire beam. So if L is the length of the beam, let's say this is point 0 and this point is L because L is the length. So we have to integrate this strain energy on the small element from 0 to L. Okay, so integral 0 to L m square by 2ei into ds. Again same, m square by 2ei is the constant. But here one more point, ds and dx. What is this ds? ds is the curved length, but here it is a straight length. Okay, so if you see for the smaller deformations, so initially it is the straight length dx. Okay, so after the application of load it has been converted like this. This is the ds value. Okay, so this straight length and curved length both are approximately same, not exactly same but approximately same. So that is why I am writing it as a ds is equal to dx. Whatever the straight length of the beam before bending and ds after bending, so these two dimensions are approximately same. That is why I am taking ds is equal to dx and I am substituting the value here. In place of ds I substituted dx. So now take out m square by 2ei, integral of 1 into x, it is x only. 1 into dx, that is x only. In the place of x we have to substitute the L value. So now we will get the final equation as u is equal to m square into L by 2ei. Okay, so this is the strain energy stored in a body when it is subjected to bending moment. Okay, so with this I am stopping today's lecture. We will continue the session in our next class. Thank you.